Okay, welcome back. We're going to continue our nomenclature chapter by looking at polyatomic anions and how do we deal with ionic compounds that are no longer simple binary structures. This one will probably be a little bit more tricky, so we'll deal with this as its own major topic. Ideally, you understand the basics of binary covalent compounds with our prefixes, and we understand the concept of how we put together neutral ionic compounds, that we need to reference the charges only of the cations if it has more than one possible oxidation state, but we usually don't reference the charge of the anion because they are understood. We'll go ahead and continue. So, polyatomic. Poly means many. Like polyamorous means many lovers. Polyatomic means many atoms. Now, most of our polyatomic ions will be anionic, meaning negatively charged. Some of these guys will absolutely need to be memorized in order to kind of remember them. But most of them will follow some degree of pattern. And so I will try to teach you the pattern. I will give you more information than you need because looking at a small picture of a pattern, you cannot see it by itself. But if you try to look at the complete picture, usually you can get a very good idea. Now, just note, this is a little tricky, so we will work through it hopefully slowly. The most common type of polyatomic anions we'll see is oxyanions. They are a mixture of nonmetal or metals bound to enough oxygens to make them an anion. Basically, the metal or nonmetal in the center adopts a cation-like charge, and the oxygens adopt the -2 charge, and we bind enough oxygens to them to give the overall structure an anionic charge. Just as SO3, sulfur trioxide, was a neutral binary covalent compound, SO4 becomes sulfate, and it's now an anion rather than a neutral covalent compound. So, just some examples. We see sulfate, we see nitrate, we see nitrite, we see perchlorate, we see permanganate. All these with some amount of oxygens, a negative charge, and either a metal or a nonmetal coming first, as in the cation position. Now, most of these oxyanions will have 2 or more possible combinations of oxygen. Because they have 2 or more possible combinations of oxygen, but the same charge, we need to designate them differently. Most of the oxyanions we will deal with no longer adopt the IDE ending. Because of that, they're going to change to an ate ending or an ite ending. Ate is always the bigger option. Ite is always the smaller option. So regardless of how many oxygens we see bound, ate is more, ite is less. I ate too much is the big one. Just a single bite is a small one. So ate is the big, ite is the small. Now, here is this massive pattern. I want to first go through it and then explain it. We see for boron, we have borate, BO3, 3-. Moving to the right, we have carbonate, CO3, 2-. we have nitrate, NO3, 1 minus. And we see not oxate, but no normal oxate because it's hard to have oxygen in the center, but we have peroxide, which is O2, 2 minus. And there's no oxyanions whatsoever for fluoride. And we'll discuss that more in a little bit. In nitrate, we also have a NO2, 1 minus. Nitrite. Note that the charge of the nitrate and nitrite are the same. Moving down to the next column. Aluminum, remember, is a metal, not a non-metal, so we skip that guy and we move to silicate. SiO4, 4 minus. Notice 4 oxygens as opposed to 3 oxygens the row above it. We have phosphate, PO4, 3 minus. We have sulfate, SO4, 2 minus. And we also have sulfite with SO3, 2 minus. And chlorine, we get perchlorate, ClO4, 1 minus, ClO3, 1 minus, chlorate, ClO2, 1 minus, chlorite, and ClO, 1 minus, hypochlorite. Moving down, arsenate, arsenite, kind of similar to phosphate and phosphite. Well, we don't see phosphite. Then we move across selenate, selenite, similar to sulfate and sulfite. And we see perbromate, bromate, bromite, hypobromite, identical to the chlorine. One more row, tellerate, tellerite, similar to selenate, selenite, and sulfate, sulfite. We see periodate, iodate, iodite, hypoiodite, similar to chlorine and bromine. So, what things can we take away? 1. Row 1 does not go above 3 oxygens. Does not go above 3 oxygens. But we see the charge is going down from 3 to 2 to 1. Why does it not allow more than 3 oxygens? It has to do with, 1, the generalized size of the atoms. The boron, carbon, and nitrogen are significantly smaller than the silicon, phosphorus, and sulfide that we saw when we looked at the periodicity. Also, got to remember, row 2 has access only to the s and p orbitals. Once we fill the p orbitals with electrons, we have achieved a noble gas-like electron configuration. There's no other place to put any extra electrons. We do not have low-lying energy orbitals. You'll note that oxygen and fluorine do not have oxyanions. If we followed that trend, borate, carbonate, nitrate, oxygen would have been neutral, as we see in ozone, and fluorine would be positive. So these are no longer oxyanions. It's really that the oxygen needs to be more negative than the center atom. But in oxygen isn't more negative than oxygen. And fluorine is definitely not more negative than oxygen. So they do not achieve oxyanion status. As we move down, we see silicate. How is silicate different from carbonate? Well, we added 1 oxygen and it gained another -2 charge. Remember, oxide is 2 minus. If we were to add 2 to 2, we get 4. So when we add 2 minus onto 2 minus, we get 4 minus. The similar pattern when we add 2 minus to 1 minus in nitrate to phosphate, we get 3 minus. If oxygen was a neutral, when we add a 2 minus to it, it becomes 2 minus. And if fluorine was positive 1, then if we add a 2 minus to that one, it becomes negative 1. There is a note that phosphite technically should exist but does not exist by itself. But it can exist when hydrogen is involved. So we do see a hydrogen phosphite, and we'll talk about that in the next slide. But just note that phosphite should technically exist, and it's just PO3 3 minus. But, okay. So why can row 3, row 4, row 5 all have 4 oxygens when row 2 could not? That has to do, one, the atoms are bigger. They're larger, so they're able to fit the oxygens around them. And second, they have empty 3d orbitals. Remember, row 3, you start to fill up the 3s, you fill up the 3p, and you have an empty 3d. That 3d orbital doesn't start to get filled until the 4th row. But until that time, it is essentially the empty attic or the crawl space of your house. It's not filled with anything important, but if you're like, oh crap, someone just gave me all this furniture that I can't use, where you're going to do it, you shove it in the crawl space. You shove it in that 3d orbital or that 4d orbital, and that's where those extra electrons are capable of going. And that's what we see when we see these 4 oxygens. Now, the other thing to note is chlorine, bromine, and iodine all have 4 possible structures. And so we have to further designate these 4 possible structures as differently. They cannot have more than one 8. We cannot have more than one 8, or else we're going to get some confusion. So we're going to add a prefix onto these based on some, I'm pretty sure, Latin terminology, maybe Greek. Ugh. But this is some biological, medical terminology that you've heard of. We say hypo. Hypo means under or below. A hypodermic syringe goes under the skin. We have a hypothermic patient. He has a decreased temperature from being out in the cold. Hypo means below, so hypochlorite means having an oxygen that is below that of chlorite. Below chlorite is what hypochlorite means. Well, we're not really used to a but we are used to, or maybe you've heard of, hyper. Hyper, he is elevated energy levels. Hyperthermic is the old way of referring to a fever, where you have an elevated body temperature. However, in order to avoid confusion, we abbreviate hyper as just per. So perchlorate means above or elevated above chlorate. So chlorate and chlorite still are upper and lower, but perchlorate means above chlorate and hypochlorite means below chlorite. And that is how we're going to distinguish those 4 possibilities. And that's going to hold true for all of our group 7 except for fluorine. Now there are a few other polyatomics. Some of these are ones where we add in a hydrogen to them. This is on the way to become an acid, which we'll talk about in the last video. But hydrogen is typically +1. It's +1 because it is in group 1A. So typically plus 1. So when you add this to an anion, we are decreasing the negative charge by 1 unit. How do we name this? We name it by adding hydrogen prior to the anion's name. So HCO3 1- becomes hydrogen carbonate. The common name is bicarbonate, but hydrogen carbonate is the proper way to name this. The same thing with sulfate. When we add a hydrogen, it becomes hydrogen sulfate. Bisulfate. Now, hydrogen phosphate, because phosphorus is 3-, it becomes HPO4 2-, hydrogen phosphate. However, because one more does not make this neutral, we can add a second hydrogen, and that becomes dihydrogen phosphate. So 2 hydrogens and a phosphorus and the phosphate. We can do the same with hydrogen sulfite and hydrogen phosphite, but it's the same general idea. Now, we won't use many of these metal oxyanions, but they are there and they follow similar patterns. Manganese adopts a similar setup as chlorine, and so just like we have perchlorate, we get permanganate. Chromate adopts a similar setup as sulfate, and so chromium, and so it becomes chromate. And we can have a weird one, dichromate, but that is a weird thing. And then finally, we have a couple exceptions that you may just need to learn. We will learn some of these. We will see some of these. I've given you the 3 most common ones that we really need to make sure you learn. Just like water is hydro, oxygen by itself is oxide, so it's not hydrogen oxide. We call it hydroxide, OH-. OH 1-. Why is it 1-? Well, oxide is 2-, add a plus, and it becomes 1-. Hydroxide, that's one that will come up so many times, it's not even funny. CN is cyanide. Cyanide. We'll learn more about cyanide later, but just CN, that's a typical poison. It often gets used. Murder mysteries. This one can be written in multiple different ways depending on how you put it together, whether you put it just straight up molecules, the atoms, the elements, or how it actually appears in the structure. Depends on how you rearrange it. But C2H3O2 is called acetate. It is the only really organic molecule that is used a lot in our inorganic general chemistry. Acetate. Acetate. You could look at a CH3 group bound to a carbonate, which is a COO1-. There's a few others. Oxalate, which is 2 acetate, basically 2 carboxylates together, but we don't usually use oxalate. Now, this is the tricky one that you should look out for, but no, it is rather rare. It is not an oxide, it is a peroxide, one above an oxide. Note, if oxide is 2-, peroxide should still be 2-. What happens is these 2 oxygens are bound together in such a way as to not change the overall charge, but change how the binding is going. This is often used when we talk about hydrogen peroxide. But just note, whenever the oxygens don't add up to 2-, it could be a peroxide. And the last one is the only polyatomic cation we will use on a regular basis, and that is ammonium, NH4 plus. Well, if N is 3 minus and we have 4 plus 1s, a 3 minus and 4 positive 1s adds up to positive 1, which is ammonium. Typically, all polyatomic cations get an IUM ending, but we don't use enough of them that it's going to matter. So ammonium is the only one we will see on a regular basis. Note, these guys still must become a neutral compound. And so you'll just use the names as opposed to other factors of identifying them. Recognizing these structures will be the key. But okay, let's go ahead and do these 2 slides worth of practice, and that will be this video. So start up here. Recognizing and breaking it down. I'm going to break it down cation anion pairs. Cation anion pairs. Metal oxyanion. So metal potassium, because it is group 1, it's just potassium. OH, it's not oxide, it is hydroxide. We don't have to label how many of each, it is assumed it's neutral. So potassium. Na, it's sodium. We don't have to label it's 2. SO4, so there's 4 oxygens. S is here. We either have a possibility of 4 or 3. So Sol, we have 4 instead of 3, so it's ATE. It's the larger ending. It's not sulfite, it is sulfate, because it's the higher quantity. It's just sodium sulfate, because we don't need 2 of them. Zinc, our weird, stupid exception. So zinc, we don't need to label it zinc 2. It's just zinc. ClO3, so it's a chlorine. Now there are 4 possibilities. There's 4, 3, 2, 1. The top 2 are 8s, the bottom 2 are ites. So it's a chlorate. Now, since this is ClO3, it is chlorate. If it was 4, it would be perchlorate. But because it's 3, it's just chlorate. So zinc chlorate. We don't need to reference this 2 because it is assumed zinc is 2 plus. Now, hydrogen is not technically a metal, so this is, we got our metal. Magnesium, Mg. This PO3, so it's 3. It's a phosphite, the smaller number, and we have 1 hydrogen. So magnesium, hydrogen, phosphite. Do I need to reference how many magnesiums? No, because we're saying we have 1 hydrogen, and we assume the amount of magnesiums makes this neutral. The amount of magnesiums makes this neutral because it's 3 minus, 1 plus, 2 plus. 1 and 2 is 3. 3 minus 3 is 0. It's already assumed. Okay, this one's a little bit harder. Going backwards, you have to know something about the charges. Cesium, that's plus 1. Cyanide is minus 1. You need to know that cyanide is minus 1 in order for this to work. But 1 and 1 makes CsCN. Magnesium is 2 plus. Acetate is 1 minus. And so, and this is C2H3O2. So I need to put that in parentheses, and it becomes 2. That's not easy. Don't forget the easy stuff. So Rb, that's plus 1. Nitride is just -3. It's N. So it's just Rb3N. It's not an oxyanion. It's just regular. And ammonium, NH4 plus. And chloride is 1 minus, so NH4Cl. You have to remember some of these guys in order for this to work. If you don't, it becomes a little harder. Okay, let's look at some of these, turning them. Some more practice. So, split these guys up. Just a reminder, the whole shebang. Sodium. Sodium is not really anything special, so it's just sodium. We have 1 H, so hydrogen. And it's PO4, so it's phosphate rather than phosphide. Do we need to say there's 2 sodiums? No, because it is assumed there's 2 sodiums to balance the hydrogen phosphate. Sulfur is group 2, 6A, so it becomes 2 minus, which means copper must be plus 2. So this, remember, when we have a not transition metal, it has to be copper 2 sulfide. Oh, so 5. Copper 2 to reference the transition metal. Magnesium. OH is our hydroxide. We just did that guy. That's ammonium chloride. We don't have to reference it. You gotta remember that NH4. It's a weird one. Ba is group 2. So barium. CO3. It's not a carbonite. It's a carbonate. Why? Because carbon is on row 2. Row 2 has a max of 3 oxygens. So carbonate is the upper limit. Same thing here. Potassium. It's with a nitrogen. Nitrogen is row 2. So 3 is the upper limit. So 4 doesn't exist. We don't see the 4. So 2 would be the lower limit. So potassium nitrite. Potassium nitrite. We don't have to reference the charge because nitrate and nitrite are always -1. Li becomes lithium. ClO4. Remember we said ClO3 was chlorate. So 1 above chlorate becomes perchlorate. Lithium perchlorate. This one's a little tricky. Transition metal, 1 minus. There's 2 of them. So this means this is 2 plus. This is Hg is mercury 2 nitrate. NO3, we have NO2 right here, nitrite. NO3 is nitrate, one above. Last 4, sodium. So notice this is the one structure that is not simplified. This is the one structure that is not simplified. Why isn't this simplified? That's because this whole thing is one unit. This whole thing is one unit, and that is peroxide. Peroxide. Otherwise, you'd be just Na2O or NaO. But because it exists like this, you have Na, Na, as opposed to NaO, NaO, like that. We have NaOO, Na. Instead of like a repeating pattern of that, it's A, B, B, A, instead of A, B, A, B, A, B, A, B. So, CS is cesium. I is iodide. Some of these are still going to be easy. You don't need a reference. Group 1, Group 7. Calcium. SO3. S is row 3. The max possibility is 4. So it's an SO3 is not sulfate, it is sulfite. K is potassium. Make sure you're reading this carefully. If you're reading the slide, it looks like this, because the I doesn't have the bars. But is there a KL element? No, there's not a single KL element. So it cannot be that. It has to be KIO. There's no L element either. So it can only be KIO. So potassium. How many oxygens do we have? We have 1. So if we can go from IO4, IO3, IO2, 1 is the lowest. So it's going to be an iodide, but it's not just an iodide, it's a hypoiodide. Potassium hypoiodide. And that will be enough for this video. We will finish up this in the last video.